Let's talk about this. So chi-square testing. Again, we're just going to give the big, brief overview, right? So it probably takes about 15 minutes or so to get this done here. And then we will move on to the next piece, which is the data set problem on this. Okay, there we go. All right, got it going. Okay, let's talk chi-squared test. So remember, the nice thing about chi-squared is we don't have to like debate, is this a test of significance or is this a confidence interval like we had last chapter? It's always a test of significance. It's called a chi-squared test, right? So you see it with the Greek letter chi. Sometimes you see it kind of spelled out, chi, and they go squared. Doesn't matter how it looks like that, but it is called chi. It is a Greek letter, chi-squared test. All right, so what is a chi-squared test doing? It is testing relationships. It's testing relationships of values. But we have two different main ideas of a chi-squared test. So chi-squared test, we don't have to, again, worry about confidence interval. We just need to worry about, should I be doing a goodness of fit test? So we call it GOF. Should I be doing a goodness of fit? Or should I be doing a two-way table test? So should I be doing a two-way test or a goodness of fit test? How are we going to know? Well, a lot of times you're just going to look at the data set, right? A lot of times they're just going to give it to you in a two-way table or they're going to give it to you in a one-way table, right? So let's start with basics. Let's start with a goodness of fit test. So first identification is this is a one-way table of data. So it's a one-way table of data, right? And what you're really always trying to do is figure out my observed values versus my expected values. Observed values versus expected values. It's literally all we're doing, but it comes from a one-way table format. So typically they just give you the table of data, but if they don't give you a table of data, they would expect you to be able to build that table of data. So it would look something like this, right? Where they would say, they would give you categories. Let's just call it A, B, C, D, E. They can give us as many categories as they want, right, of different things. And out of those categories, they should give you some observed counts. So we're always going to be kind of looking at these observed counts. So that's literally what you see. And they might put it in a big sentence for you and expect you to put it together. Or you just have this nice little one-way table of data that's like that. But now our job in a goodness of fit test is to figure out the expected values. We have to physically do that, right? So expected values, we would pop those in right here. So what are expected values? It is the sample size times the probability output that they tell you. They're going to tell you some kind of probability output, all right? And that's how we're going to find our expected values. So at that moment, once you have this table built, I typically would say, grab your calculator, and this is what you need to do in your calculator. There's only a few steps you need to do. Number one is put data into L1 and L2. Put data into L1, L2. What data are you going to put in L1, L2? Observed in L1, expected in L2. Then number two, second thing you're going to do, you're going to go find the function chi-squared GOF test in your calculator. and you're going to run that test. So put data in L1, L2. Run the chi-squared GOF test. Number 3, it's going to ask you something in there that the one thing that it asks you to calculate, it's going to ask you to calculate the degree of freedom. Remember how you find a degree of freedom for a goodness of fit test. It's just categories minus 1. Categories minus 1. Now that's different than a t-test. When you run a t-test and you have to find degrees of freedom, it's sample size minus 1. So don't get it confused. This one's a little different. It's categories minus 1. Like categories are A, B, C, D, and E. Minus 1, it's going to give me 4, right? So the degree of freedom of like this make-believe one that we have here is 4. Okay, so there's your calculator functions right there. That gets you really all the information you need, and then your job is to just fill in the pieces, fill in the assumptions, fill in the hypotheses, fill in the formula, right? Fill it in as if you were doing it yourself. So that is the calculator part. Okay, so that's really a goodness fit. You see a one-way table, you build the expected counts, go into your calculator, do your calculator stuff. But now let's talk about what do we need to write down on paper. What we write down on paper follows the format of phantoms. So let's talk about the phantoms for this chi-squared goodness of fit test. The hypotheses for a chi-squared goodness of fit test. We are always going to assume that our probabilities are as they direct them to in the problem. So you're going to usually have one of two styles of formats. You're going to have probability of A is equal to whatever number they threw at you. Probability of B is equal to whatever value they threw at you. Probability of C would be equal to whatever, so on, so forth. Right? So if they designate probabilities for each category, we are going to assume that the probabilities actually match. Right? The probabilities of all these match. Or the other standard way to do hypotheses is instead of them giving you specific probabilities, they'll use words like, are they equally proportional? Are they fair? Right? Are they the same? So if that's the case, it's going to be something like probability equals probability equals probability, and you're just going to keep going on and on and on with however many categories. So a lot of times we want to see, are all the categories the same? Sometimes we want to see, like on the left, that the categories match whatever percentages they're throwing at us. Right? And that's okay. Either of them work. But we just need to see the null hypothesis that works for that. In any case, no matter which one of the two that you use, your alternative hypothesis is usually the statement, at least one proportion is different. At least one proportion is different. We don't care which one is different. The chi-squared test itself doesn't care which one is different. It's just gonna, if it is able to reject, it's saying one of these is in fact different. All right, so that's what it looks like. So that's your hypotheses. Kind of, again, you're gonna use one of those standards, right? Always got that alternative standard. All right, let's go to the next piece. The next big piece here is what assumptions do we check for a goodness of fit test? By now, you should know there's always three checks. Shape check, random check, independent check. Right? Number one, our shape check, but it's no longer a Z, it's no longer a T. So our shape check has to be a chi-square check. And the chi-square check is just checking, are the expected counts greater than or equal to 5? Are the expected counts greater than or equal to 5? So make sure you take clear notes on that. It's expected counts, not the observed counts. Can the observed counts be less than 5? Yeah, we don't care. The expected counts need to be less than or greater than or equal to 5. Second check you're always going to do, random. You guys should know how to do that by now. Third check you're always going to do is your independence check, which is typically, or if you have no other reason not to, just do the 10% rule. Right, that's usually the independence check that you're going to do. So always shape check, random check, independence check. If I'm doing a T distribution, shape check, independence check, random check. If I'm doing a Z distribution, shape check, random check, independence check, right? Always the same 3 checks. Just the one that usually changes is the shape because you're doing a slightly different shape every time. All right, there we go. Assumption checks. All right, let's move into the next big piece there, the T. What is the T? What are we after on the T? Well, we are after the curve, right? Drawing the curve, shading the curve, showing the chi-squared. So this is kind of what it would look like. Always just draw the generic chi-squared curve, which looks like this. It's always skew right. It's the generic chi-squared curve. Always starts at the left at 0. And then somewhere along the line, you're gonna have to show your chi-squared value, and you're always gonna shade to the right. So drawing your curve and shading your curve is an important part of the T step of phantoms. If you're doing a T distribution, you'd be drawing a T curve, shading it. If you're doing a Z distribution, you'd be drawing a normal curve and shading it. If you're doing a chi-squared distribution, you're doing a chi-squared curve and shading it, right? You're always just getting used to shading that curve. And then show your chi-squared calculation. Remember, this is kind of how we show it. We show it, I'm going to give you the generic. It's observed minus expected squared divided by expected count plus the next observed minus expected squared divided by the expected count plus ... Just keep that pattern going, or literally on an AP exam, just literally write plus ... and then show your chi-squared value that's coming out of your calculator. All right, so that is kind of your H, A, and T. That's the hat part of phantoms. Those are the main important parts right now that we know. And then at this point, I'm pretty sure we know how to obtain a p-value. Look at our calculator. I'm sure we know how to make a decision, p-value versus alpha value. And hopefully by now we can summarize. Tell me what the decision means. So all of those are normal. I'm not going to go through the details of those because we've done the details many times now. So hopefully now you're just like, get me to a p-value, because when I get to a p-value, I can make a decision, I can summarize for you. Right? So that's what that looks like there. Okay, that is a goodness of fit test. Again, what am I going to do? I'm going to find the table of values. I'm going to go find my expected values, and I'm going to plug that stuff into the calculator, and I'm going to do that calculator function right there, chi-squared GOF test. Right, so if we didn't have to show the assumptions, if we didn't have to show the calculations, if we didn't have to make a decision, a problem like this should take you about 20 seconds. Right, put 2 lists together, go to GOF test in your calculator, and it will do it for you. Right, so some of the just getting it into your calculator it will save you a lot of time, but also kind of gets you to where we need to go. All right, so that's called a goodness of fit test, one-way tables. That's the stuff we need to know for it. All right. Okay, what if it's a two-way table? So let's switch gears a little bit. Two-way table. So if it's a two-way table, then we are going to be trying to find one of 2 things. Two-way table. We are either going to be doing homogeneity, a test for homogeneity, or number 2, we'll be doing a test for association. Test for homogeneity, a test for association. Well, how do I know which one is which? Well, it's really going to come down to what they are. So homogeneity, if I just had no idea, it's testing to see are multiple multiple groups producing the same proportions. That's what a homogeneity is doing. Notice, are multiple groups producing the same? The word homo means same. That's where it comes from, right? So when we see the word same, we know we are doing a test for homogeneity. Association. What is association test for? And literally it's doing the same test, right? But it's saying, are the variables from a group independent a little too big on that. Independent of each other. So that's what association is testing for. It says for independence of variables. Or another way to say independence is, are they associated? Are they associated or not? Are they independent or not, right? So those are the two tests that we're trying to run. That's the question they're trying to answer. The chi-squared is answering that question for us. Okay, so how am I know if I'm supposed to be running a two-way table test? Literally the data will be presented to you in a two-way table. All right, so two-way tables typically look something like this, where they give you some variables, A, B, C, D, and then they give you some other variables to test against it, X, Y, and Z. And then we build this thing right here, like we call this thing a two-way table. So inside this table then would be some values. And again, it's coming from a certain group, right? So again, we use stuff like across the top, it might be hair colors, right? You put yourself into a certain hair color, blonde, brown, black, other, right? Hair colors. And then maybe along the side, it's car colors, right? Red, black, silver, white, whatever, right, that we have. And you put yourself into a category from a single group. And now what we're going to ask, is there an association between your hair color and the color of your car? Right? People might want to know. So we're going to run a test, and we're going to see, is there an association of those different variables? So it will be presented to you as a two-way table like this. And I'm going to tell you, if you're taking the AP exam, if you see a two-way table, it's one of two types of questions. It is a probability question, or it is a chi-squared test of significance. They're going to ask you one of those two things on a two-way table, either a probability style question or a chi-squared. Right? So just be aware of that. And when I see a two-way table, I should be thinking those two things. Okay, two-way table. So what are the things that we need to know? Well, let's talk about calculator. What do I put into my calculator? So here's what you got to do in order to do this one. Slightly different. You got to go to your matrix function, and so you're going to put data into a matrix. Typically, on the TI-84 format, we're just going to fill in the first matrix, right? We're going to go to the matrix menu, we're going to go to edit, and we're going to put in my data. Matrix is the mathy word of saying a table, a two-way table, right? That's what a matrix is. So once you've done that, then you're going to go find the chi-squared test function. Make sure the GOF is not a part of that, just chi-squared test function. And you're good. And that's it. That is actually all your calculator needs in order to do the test. It just needs to know where is the observed matrix. I'm going to put it in A, chi-square test, and you tell it where you want the expected matrix. I typically want the expected matrix in matrix B, so I just tell it that. So that's what you do in your calculator. That will get you most of the information that you need, right? That in the calculator and go. But let's do a couple side notes here. What if we needed to find the expected count for each cell? The expected count for each cell in our matrix. And what I mean by each cell is each of those little squares that were created in your matrix is considered a cell. So how do I find the expected count for any one of those? For each cell, here's how you do it. You take that cell's row total, you multiply it by that cell's column total, and you divide it by the grand total. Right, so row total times column total divided by grand total. Right, that's what we would end up doing. So that's going to give us for each of those cells, yeah.
On some of my open math, it asks to find degree of freedom for like two-way tables, but it just gives you how many were each column or rows, and it's different than
Yeah. So let me do this. Yeah, I'll do that in just a second. I'll give you that formula. So the degree of freedom formula. So let's talk about though this for any given cell. I want to run this right here. So typically this is how you would do it, right? You come in here and sometimes on AP they'll even ask you, but let's say we were trying to find the expected count for just that cell right there, the CY cell. So what we do is we look across until we have the row total. We look down until we had the column total. We're going to multiply those two numbers together. And then you're going to divide by the grand total, which is usually sitting right here. Right? So that's it, right? That would give you the expected count for that one cell. Its row total times its column total divided by its grand total. All right? So that's expected count for any one cell. Now, we don't have to worry about that because our calculator does it for us. It knows that formula, and it does that formula, right? So we don't necessarily have to do that, but you might be aware of how it's getting that. So let's talk that next thing, like the question that was asked. What about degree of freedom? Because that's slightly different than it was for a goodness fit test. Degree of freedom for a two-way table. So recall that the degree of freedom in this is the number of rows minus 1 times the number of columns minus 1. Number of rows minus 1 times the number of columns minus 1. That's how you find the degree of freedom for a two-way table. And yeah, some of the MyOpenMaths were specific and asked for just literally, I want to know the degree of freedom is. They told you how many rows, how many columns, subtract 1, multiply them together, and you got it. Right? So that's what we're going to be looking for when we do a degree of freedom. Slightly different for a two-way table because a one-way table of goodness of fit is literally just the number of columns minus 1 because that's the number of categories there are, minus 1. So let's talk degree of freedom. What if this one, and they ask for degree of freedom? So we have 4 and we have 3. So I literally take 4 minus 1, which is 3, times 3 minus 1, which is 2. So take 3 times 2, so 6. The degree of freedom of this one would equal 6. Right, because of that. Okay, so there you go, right? So homogeneity association, two-way table, put it in our calculator, know some of the nuances that go there. So last thing we got to do, let's just talk about phantoms then. What are the phantoms on this thing? Right, the phantoms, this is as if you were doing a free response question on an AP exam, or your data set problem that you're going to be doing, or the AP classroom when we get to that on Thursday. So let's talk hypotheses. All right, let me do two styles of hypotheses here. So big hypothesis. What is the null hypothesis if we are thinking homogeneity? If we're thinking homogeneity, then our null hypothesis will have some context, but then it'll eventually have the word same in that context. Right? Portland, Westland, Lake Oswego, and Tigard all have the same proportion of high school graduates, right? That might be it, right? So we're always going to use the word same if it's homogeneity in our null hypothesis. So our alternative hypothesis will always have some context and we'll have the word different in there. Now, it doesn't matter how they structure their question. They could use the word different or same in their questioning. We just know that same always goes in the null. Different always goes in the alternative. Okay, so that's homogeneity. Or we'll be doing a null hypothesis for association. So if it's association, what's our null hypothesis look like? Our null hypothesis will be a bunch of words. And somewhere in there, we're going to say the words not associated. Right? So not associated. So we'll use those terms there. So it might say that we believe that hair color and car color that you drive are not associated with each other. Or you might decide to use the other word for not associated, the statsy word, is called independent. Right? So you can use those interchangeably. The words not associated means to be independent of each other. Okay, so that's going to be your null hypothesis. So your alternative hypothesis then is just going to be the opposite of those. If you use the word not associated, then the alternative is going to say, well, they are associated with one another. And then context. Or your alternative hypothesis, if you use the word independent, then we're going to use the word dependent on one another. Okay, so we're going to use one of those two things there. So that's the two different styles. You either have homogeneity or association. How am I going to know which one to use? Read the question. A lot of times the question will tell you which one you should be using, right? Homogeneity or association. If you need a secondary check, I'm going to tell you right now, homogeneity means that they took multiple groups or multiple samples, right? That's how we know we're doing homogeneity, because they had group 1, group 2, group 3, group 4, and we're trying to see, are they all the same? Or they went and took a sample from Portland, LO, Tigard, Westland, Oregon City, right? We took multiple samples from multiple groups. That's going to be homogeneity. Where association, if you need a little side check there, it's gonna be variables from the same group or sample. So it's going to just be one giant sample. We went and sampled 100 students from Lake Ridge. It'll be variables from the same group or sample. That's kind of a side check. Do we need to do the side check? No. If they use the word in there, then use the word back at them. That would get you the hypotheses there. All right, so that's what we're looking at. So the null hypothesis, alternative hypothesis for those. So let's talk real quick. What's the assumption check? It's those same 3 assumption checks we just talked about, right? Are the expected counts greater than or equal to 5? Did they check random? Did they check independent? Right, assumption checks. That's exactly the same as it was goodness of fit test. So if you don't want to write it again and you just want to point at your goodness of fit test, that's exactly what it looks like, right? What about the T? Looks just like the goodness of fit test. It's going to be a skew right curve. You're going to find your chi-squared value on there. You're going to shade to the right, and it uses the exact same formula. Observed minus expected squared over expected plus ... Just keep it going for every single cell. Right? So like my formula, if I were to do it by hand, hang on real quick. If I were to do it by hand, I'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I would do that formula 12 different times, like I do the observed minus expected squared over expected plus observed minus expected squared over expected. You do that 12 different times, and you can add them all together. So don't do it by hand. Do it in your calculator, right? Because it can get really large, and it can be exhausting at some point. So do it in your calculator, but fake it by writing it on your paper. Writing the first set plus ... And then obtain a p-value, make a decision, summarize. Of course, that's the same stuff that we've been doing since chapter 9. So hopefully you feel good about that. I see a p-value, I make a decision, I can summarize. All right? There's our phantoms. We do not have to worry about panic in this chapter. It's all phantoms. What's the hypothesis? What's the assumptions? Put it in my calculator. Throw the formula together. Find the p-value, make a decision, and summarize. Every single time. This is what you're going to be doing. Know some of the little nuances, like how do you find expected values? How do you find degree of freedom? If you got that and you know how to use your calculator, it doesn't take too long at all to do these problems. All right? So that's what we got there. That is the overall piece of our chi-squared test. It's literally trying to figure out which one do I do, goodness of fit or a two-way table. And usually it's pretty clear once you look at the data set because they put it in the right form for you most of the time. All right, so what we're going to do, we're going to move on to our data set problem.